Hello and welcome to the Medicaps learning series. I am Dr. Shalini Sharma, Assistant Professor in Department of Chemistry. Today I am going to explain the concept of hybridization with some suitable example. So let's start with our today's topic. Let's start with our today's topic, that is hybridization. First of all, this hybridization concept was introduced in 1931 by Linus Pauling. Behind the introduction of this hybridization, this Pauling introduced this topic to explain the structure of covalent compound which could not explain with the help of VBT theory. So we can say that to overcome the VBT theory, this hybridization concept was introduced. Now what is hybridization? What is the requirement of this hybridization? The hybridization is mainly required for the chemical bonding in so many covalent compound. So we can say that the chemical bonding is sometimes cannot be possible without the hybridization process. So what is the definition of this hybridization? Hybridization is the intermixing of atomic orbitals to form the new orbitals with equal energy and identical shape and size. So this is the definition, and in this intermixing of atomic orbital, the new orbital will form with equal and identical shape and geometry. So this is the basic concept of hybridization. Let's discuss the types of hybridization with some examples. Now before the types, there are some conditions which are required for hybridization. There are mainly two conditions. The hybridization is only conducted by the central atom of covalent compound. And another condition, the number of atomic orbital which participate in hybridization is always equal the new hybridized orbital. So we can say that the before hybridization, the atomic orbital, and after hybridization, the new orbital, the number should be same. What is the importance of hybridization? Why do we need this hybridization? So first is to predict the geometry of covalent compound or covalent molecule, or we can also explain the structure, shape and bond angle of different atomic orbitals in any covalent molecule of compounds. So let's start with the types of hybridization. Now the types of hybridization: sp3 hybridization, sp2, sp, sp3d, sp3d2, sp3d3 and dsp2. There are so many types of hybridization, but today we are going to discuss these three hybridization because these three hybridization are the basic hybridization which is mainly required for so many covalent compounds during the bond formation. So first is sp3 hybridization. Now in this sp3 hybridization, 1s and 3p orbital of central atom take part and intermixed with together to form the 4sp3 hybridized new orbital. As I told you, before the hybridization, the number of orbital must be equal to the after hybridization. So 4 atomic orbitals are taking part, 1s and 3p, and after the hybridization, resultant 4sp3 hybridized new orbital will form. For example, we know that the s orbital is spherical in shape, and p orbital, there are 3 p orbital, px, py and pz. In sp3 orbital, 1s and 3p orbital will take part and they intermix together. After the intermixing, after the hybridization, resultant, the 4 new hybrid orbital will form. These 4 new hybrid orbital are tetrahedrally arranged in the space with the bond angle of 109 degree and 28 minute. In this hybridization, each and every orbital, the new orbital, possess the sp3 characteristics. It means each and every hybrid orbital has the sp3 characteristics. So we have like this, we have 4 hybrid orbital. And this each and every orbital, the percentage of S is 25% and percentage of P is 75%. So this is the geometry of sp3 hybridization. Now by taking the example of CH4, we can also explain this sp3 hybridization. So let's take an example of methane. We know that methane is the first member of alkane series. Now in this methane, the carbon is the central atom. Now its atomic number is 6. Its configuration is 2 and 4, 1s2, 2s2 and 2p2. This configuration we can write in the form of orbital diagram. In ground state, 1s2, 2s2, 2px1, 2py1 and 2pz is vacant. So according to VBT theory, we have already known that only the valence electron, only the valence shell will take part in process of bonding or in hybridization. So this 1s2 will not take part in any type of process of intermixing of orbital. So only we will take 2s2 and 2px1 and 2py1. So after the mixing of this 2s2 and 2px and 2py, but before this the condition is that one orbital, one electron, Let's take an example of sp3 hybridization with the help of methane. In methane, the formula is CH4, the carbon is the central atom and its atomic number is 6. Now its electronic configuration is 2, 4, 1s2, 2s2 and 2p2. In ground state, the orbital diagram is 1s2, 2s2, 2px1 and 2py1. 2pz is vacant. As we know, according to the valence bond theory, only the valence orbital will take part in bonding in chemical formation, but the inner orbital will not take part. So these 2s, 2px and 2py will take part in hybridization. But before the hybridization, this one electron is get excited from 2s2 to 2pz, and now this is the excited state. After the excitation, we will get 2s, 2px1, 2py and 2pz. So each and every orbital possess the single unpaired electron, which is important condition for any type of bonding. So we have 4 orbitals, 1s and 3p, and this 4 orbital will take part in sp3 hybridization. The intermixing will take place. After the intermixing of these atomic orbital, we will get the 4 sp3 hybrid orbital. This 4 sp3 hybrid orbital are tetrahedrally arranged with each other with the bond angle of 109 degree 28 minute. After the sp3 hybrid orbital formation, now for this methane, carbon is ready to form the bond with 4 hydrogen. Now after the 4 sp3 hybrid orbital, 4 hydrogen with single electron start overlapping with 4 sp3 hybrid orbital. We know that when the head-on overlapping takes place, the sigma bond will form. So after the 4 hydrogen bonding with 4 sp3 orbital, we will get the CH4, that is methane. And we will get the 4 sigma bond due to the head-on overlapping of 4 hydrogen with 4 sp3 orbital, and that's why the shape of methane is tetrahedral and bond angle is 109 degree 28 minute. So by this we can explain the sp3 hybridization, and not only methane, all alkane possess the sp3 hybridization. So let's start with the another, that is sp2 hybridization. Now similarly, as we have been discussing sp3, in sp2 we have 1s and 2p orbital. If 3 orbitals are participating in hybridization, the resultant hybrid orbital will be 3. So 1s and 2p. 2p means 1 px and 1 py. The resultant 3 sp2 orbital we will get after the intermixing. The shape will be trigonal and bond angle will be 120. So this is the hybridization due to the 1s and 2p. Let's take an example of this sp2 hybridization with the help of BF3. BF3 is boron trifluoride. Now in the boron trifluoride, boron is the central atom and its atomic number is 5. Now its configuration is ground state condition. The configuration is 1s2, 2s2 and 2p1. This is the orbital diagram, 1s2, 2s2 and 2p1. In this boron, the py and pz orbital is vacant, and for the hybridization, the one electron from 2s is get excited into py. So this will be the excited state is 2s1, 2px1, 2py1 and again 2pz will be vacant. So we have 3 atomic orbital, 1s and 2p, and these 3 atomic orbital intermix with together and to form resultant 3 sp2 hybrid orbital of boron. These 3 sp2 hybrid orbital of boron are ready to form the bond with 3 fluorine, and now with this 3 sp2 hybrid orbital, 3 fluorine overlap, head-on overlapping will take place and the 3 sigma bond will form, and by this we will get the boron trifluoride, that is BF3. That is BF3. In this, boron is the central atom and 3 fluorine. This is the bonding of BF3. So this is all about the sp2 hybridization. Let's take another example of sp hybridization. Now in sp hybridization, 1s and 1p orbital. If the 2 orbital are participating in hybridization, the resultant, the 2 hybrid new orbital will form. After the intermixing, the 2 hybrid orbital will linearly arranged and bond angle is 180. Now in this sp hybridization, both the hybrid orbital has the characteristics of s and p. S percentage is 50 and p percentage is also 50 and bond angle is 180. Let's take an example of this sp hybridization with the beryllium difluoride. Now in this BeF2, beryllium is the atomic number, its atomic number is 4. Atomic number is 4 and its configuration is 1s2, 2s2. Now in ground state, 1s2, 2 electron in s orbital, 1s orbital and 2 electron in 2s2. But the p orbital is completely vacant. But for the hybridization, as we know, the single electron, the unpaired electron is required. So the transfer of one electron from 2s to 2px will take place, and then we will get the two atomic orbital s and p. These two sp orbital will intermix together and to form the resultant new sp hybrid orbital. And this new sp hybrid orbital, this is sp and this is again sp. Now they are ready to take part in the bonding with 2 fluorine. We know that fluorine, for example, Fe beryllium with, so bonding will take place, and this fluorine will perform the head-on overlapping with each and every sp hybrid orbital of beryllium, and due to this head-on overlapping, the sigma bonding will take place, and bond angle 180 and shape is linear. So this is the bonding of BeF2 with the help of sp hybridization. So this was the today's session on hybridization. So stay tuned for more PCM basics on Medicaps learning series. Thank you.